Alright, so before we were looking at graphs of rate functions that were like flat lines and such. So when we got the area underneath the curve, we could just divide them up into like rectangles and triangles and easily calculate the area. So if I wanted to get the area under this function, that would be rather easy, just like because I can just split it up into geometric shapes that are easy to calculate the area for. But what about I had a smooth curve? Well, there's a way that we can approximate the area. It's not an actual specific exact area beneath the curve, but if I wanted to find out an approximation for the area between, I guess, 0 and A, I could make up rectangles that approximate this area. So I would get the area of this, this, and this, and that's approximately the area underneath the curve, because rectangles are easy to calculate the area for. It's just length times width. However, I missed out on these parts. So this one would be an under approximation, or an underestimate, just because the area of the rectangles is actually going to be smaller than the actual area under the curve. Hopefully you can see that. If not, let me know. But right now we're going to approximate area underneath smooth curves by using rectangles. And there's a couple different ways to do these rectangles. Let's just, I'm going to say some stuff, and it might not make sense. I don't know. But I'm going to say some stuff, and then we'll see what happens. Afterwards, we'll do a bunch of examples. This stuff, I want you to write down. The other stuff, maybe not so much, but I'll tell you when you don't have to write it down. So here, for smooth curves, we use rectangles to approximate the area underneath. So that's pretty much what we're doing in that case. We're approximating the area underneath by using rectangles. And there's different ways that you can approximate this area. Like these are, eventually we'll get to it, but they're called Riemann sums. This guy Riemann, he's just like, well, we can do this, and so like they call it Riemann sums because you're adding up the areas of the rectangles, right? You're adding. That's why they're called sums. So let's see what there's three basic types of Riemann sums. Rn is called a right Riemann sum with n subintervals. So let me give you a quick example of that. If I had, say, a curve, just like before, and suppose I'm only thinking about from 0 to A again, 0 and A. Let's say 3. So R3 would be the right Riemann sum with 3 rectangles. So I have to approximate the area underneath this from 0 to A. I mean, that will be specified every time, but I'll approximate this with 3 rectangles where the top right corner of each rectangle touches the curve. So that's why it's called a right Riemann sum, because the top of the right side of the rectangles touch the curve. So if I draw a rectangle here, I'm doing 3, so I'm just going to split this up into 3 portions. And my first rectangle would be that. The top right corner is touching. Again, the second one, the top right corner, is touching. And again, so that's 3 rectangles that I'm using to approximate the area underneath this curve. And the right top corners touch. In this case, this is an overestimate because we're getting too much area, right? So, yeah, that's a right Riemann sum. A left Riemann sum, Ln, is simply the same thing. A left Riemann sum with n rectangles. The top left corner touches the curve. So that's a left Riemann sum. I'm going to draw a picture for that using the same function from 0 to A, whatever that is. In this case, the left sides have to touch. So here I wouldn't go up and then over because that would be the right side touching. Maybe I'll start on the left side then. The left side touches. I'll split it into, three areas. 1, 2, 3. If I'm doing L of 3, like L3, that means the left side will touch the top of my, or the top left corner will touch my curve. I keep missing. That's close enough. So there, the left side touches, right? The left side touches, and left side touches. And in this case, this is an underestimate because we're missing out on some actual area there. So this would be an underestimate. So like if I had a decreasing function, real quick, if I had a decreasing function and R3, that would look like this, right? That one's pretty close. This one would be an underestimate now. Here it's an overestimate, here it's an underestimate. We know, like, when it happens when you have a decreasing function, and, I mean, if you just draw it out, and you'll be able to see whether it's an overestimate or underestimate. This is still R3, but in this case, since the function is different, we have an underestimate. But that's just extra stuff. All right, and then the next basic Riemann sum is the midpoint rule. So midpoint Riemann sum, that would be, well, I mean, we take a guess. It's just the middle of each rectangle touches the curve. So if I draw the same curve that I had before from 0 to A, again, those will be specified in each one of your problems if you're trying to see this stuff. So from 0 to A, and I'm going to split it into, well, I guess if I'm doing M3, I'm going to split it into 3 equal, I mean, they don't always have to be equal, but 3 divisions, right? And in this case, the middle, right? So I have to go in between here, not on the right side or the left side. I'm going from the middle, so that's up to there. So that's gonna be where the rectangle touches, and I'll take the middle of this one. So I draw that up, and then that's where the rectangle touches. And the middle of this one, and that's where the rectangle touches, right? So I shouldn't draw that line. So this would be, oh well, it's kind of hard to tell if it would be an overestimate or an underestimate, just because you take some extra area and then you lose some area. So this one would actually be the closest approximation. Here we're losing some area, right? We don't count for this, but we count extra in that top corner. We lose some of this, we count extra for that. So they kind of almost balance each other out. Doesn't always exactly balance each other out, but this, the midpoint Riemann sum, is always going to be closer if you're using the same number inside. The midpoint Riemann sum is always going to be the most accurate. It's going to be the middle. I mean, it's like if we have the same curve and we do all 3 different rules, one of them will be an overestimate, one of them will be an underestimate, and then one of them will be the closest approximation. I don't know. It's harder to tell. Like, I don't know if this is an overestimate or an underestimate. So I do know that it's closer, though. It's just it's harder to tell that way. But there you go. So I think I'm going to end this video because it's kind of long. I want you to write all this stuff down. In the next video, I'm just going to do a bunch of examples.